multi-degree of freedom vibrations today. Some matrix algebra first. Let A be symmetric and real, then the eigenvalues of A are real and the eigenvectors can be orthogonal. That means they are orthogonal when they are not repeated, and when they are repeated they can be chosen to be orthogonal. Why is this true? So let Ax be equal to lambda x, that's one eigenvalue and the corresponding eigenvector, and we can take the complex conjugates of all quantities and that's still true. But because A is real, this equation here implies this equation here. So Ax conjugate is lambda conjugate x conjugate. I can take this equation here and pre-multiply by x conjugate transpose, and I get that is equal to lambda times this quantity here. If you know complex conjugates, you know that this quantity here is the sum of the squares of the absolute values of every element of x. Since x is not 0 by definition, this is a positive quantity. But notice that we can do the same on this side here. So x transpose A x conjugate by a similar calculation is lambda conjugate times the same positive quantity. But over here I can transpose it, and because A is symmetric, I get basically this quantity, and therefore this one here is the same as this one here, which means lambda is lambda conjugate. That means the eigenvalues are real. The eigenvectors are a little more interesting. Let x be an eigenvector, let y be perpendicular to x, that means y transpose x is 0. Then we can find easily that Ay is also perpendicular to x, because Ay transpose x is y transpose Ax, and Ax is lambda x, so this is lambda times y transpose x, and that is 0. You may wonder what happens if lambda is equal to 0, but this is not really a problem, and if you like you can add the identity matrix to A to shift this lambda from 0 to 1, and the eigenvectors don't change, and I am not going to get into this, but basically lambda equals 0 is not a problem. So given x is an eigenvector, we can choose a basis in n dimensions where x is one of those basis vectors and there are n minus 1 other basis vectors, which I can arrange in this matrix Q, n minus 1 of them. So this is n by n minus 1, it's a rectangular matrix, this Q. I can orthonormalize these so that Q transpose Q is identity, n minus 1 size identity. Q transpose x is 0 because this is an orthogonal basis by choice. Y perpendicular to x means y is equal to q xi for some xi, and if we know that y is in fact perpendicular to x and y is q xi, then of course we can find xi very easily by pre-multiplying with q transpose, because over here we get q transpose q, which is identity. Alright. We know that Ay is perpendicular to x, that means A times q xi for some xi is perpendicular to x. A q xi is therefore q times some nu xi, and we can find the nu xi by pre-multiplying this equation and this equation with q transpose, which means xi nu is q transpose A q times xi, and this is just some other matrix P which is symmetric and is n minus 1 by n minus 1. And so whatever arguments we applied above can apply to this n minus 1 dimensional matrix. We can find its eigenvector, one eigenvector, and that eigenvector corresponds to some xi. In the original coordinates we have to multiply by q and we get something that is perpendicular to the x again, and in this way we can go down in dimension from n to n minus 1 to n minus 2 all the way to 1 dimension, and we can construct a sequence of orthogonal eigenvectors. This shows that the eigenvectors are orthogonal. Now let us consider a conservative n degree of freedom mechanical system using the Lagrangian formulation. So we will need only the kinetic and potential energies. Let the generalized coordinates be x1, x2 up to xn. When I write just x, I mean this set of all of them, or a vector or a column matrix. From the context it will be clear. And let the equilibrium be at x is equal to 0. This we can do without loss of generality because we can subtract the equilibrium values and define a new variable. So equilibrium means del V del x k is equal to 0 for every k. So V, the potential energy, as a function of x can be expanded locally in a Taylor series, multidimensional. So we get some V0, which is the value at x is equal to 0, and there won't be any linear term because of this equilibrium condition, and the quadratic term is there and higher order terms are there, which we will neglect. In the quadratic term, it is a sum of just xi, xj with coefficients kij, and the half is for convenience. Since I am interested only in the sum, because Lagrange's equations depend only on the total potential energy, therefore I don't have to distinguish between kij and kji, and I can assume that they are equal. Similarly, the kinetic energy is quadratic in velocities, so it is xi dot xj dot times some coefficients mij which depend on x, but by a similar argument I can set mij is equal to mji, and then we note that for small vibrations we need the Lagrangian to be accurate up to second order only, because the Lagrangian we have del L del x dot, second order becomes first order, del L del x, second order becomes first order. We want the equations correct to be first order only. For this reason, we need the kinetic energy to be accurate up to second order only, and the xi dot and xj dot is already second order. Therefore, the mij's dependence on x need not be retained, and we can just put the zero value. We can put mij at whatever it is at the equilibrium value, and then it just becomes a number. After we do this, this kinetic energy, which was this sum here with x equals 0 put over here, is of the form half times x dot transpose capital M x dot, where this capital M is a symmetric and positive definite matrix, and the potential energy is half x transpose kx, where k is a symmetric and positive semi-definite matrix. Why is this one positive definite? It's positive definite because if it was not positive definite, in that case it would be possible to have non-zero velocities without having a positive kinetic energy. That's a contradiction. Over here, why is this positive semi-definite? Well, it doesn't actually have to be positive semi-definite. Here are some 1D cartoons that will help you think about it. If you have an inverted, if you have a bowl with a little ball in the bottom which oscillates, then over here it is going to correspond to positive eigenvalues. Unstable equilibria like this would lead to k not being positive semi-definite. It would have negative eigenvalues, but we are discounting them because we are interested in vibrations. But we are including the borderline case of where something can move without having a restoring force. So if you have something that slides around on a horizontal table, it is allowed in our formulation when we put this greater than equal to sign over here. Lagrange's equations, we define the Lagrangian as t minus v as usual, and these are Lagrange's equations. We do this for every k. So for k equals 1, we get one little k, index k. So for little k equals 1, we get one equation, little k equals 2, we get another equation. If we stack all of those together and write them in matrix form, we get this matrix equation, which is capital M x double dot plus capital K x is equal to 0. This is a matrix equation. Now, if there are non-conservative forces, we can include them in the form of generalized forces, and then the equation will have this form, mx double dot plus kx is equal to capital Q of t, where capital Q is a column matrix with capital Q1, capital Q2 and so on. And sometimes the Q or the non-conservative forces will include viscous damping, and sometimes we may write mx double dot plus cx dot plus kx is equal to Q. This is still a matrix equation. This is linear viscous type damping, linear damping. C is a matrix, and sometimes in this, let's look at the unforced and undamped system and seek exponential solutions as usual. That is, x is u e to the I omega t. This omega is to be found, and this u is a column matrix, that is a constant. It is not varying with time. When we substitute this into the equation, we get minus omega squared m plus k, the whole thing, times u is equal to 0. This is the generalized eigenvalue problem. We will return to this soon, but first let us do a side calculation. So m is symmetric, therefore it has real eigenvalues and orthogonal eigenvectors. So this is the matrix of eigenvectors here, it's orthogonal. The real eigenvalues are in fact positive because m is symmetric, positive, definite. And so we can define m to the minus half like this. See, this is very similar to the form of m, only lambda has been replaced with lambda to the minus half, defined as 1 over square root of lambda 1, 1 over square root of lambda 2 along the diagonal, and zeros elsewhere, and you can check by substitution that m to the minus half times m to the minus half is in fact the identity matrix. We will need this now, and also that m to the minus half is symmetric. Now let x be m to the minus half times y, where y is something new. This is a change of variables. In terms of variable y, you see m x double dot becomes m to the minus half y double dot and so on. So this is our new equation. We pre-multiply it with m to the minus half transpose, which is just m to the minus half, and so we get y double dot plus m to the minus half k m to the minus half. Let's just call this P, some symmetric matrix. P is P transpose, and so this system of equations in terms of y is y double dot plus py equals 0. The corresponding eigenvalue problem over here just has P. So those of you who are not familiar with the generalized eigenvalue problem can see here that because P is symmetric, there are orthogonal y eigenvectors. Each such motion corresponds to an x motion, so you know there are corresponding x eigenvectors, but they are possibly non-orthogonal. They do satisfy a different kind of orthogonality, and let us consider it now. So let omega 1 be one such eigenvalue and u1 the corresponding eigenvector, and omega 2 be another eigenvalue and u2 the corresponding eigenvector. So this equation here is written like this for the omega 1 u1 pair and the omega 2 u2 pair. This one, first one can be pre-multiplied with u2, the second one can be pre-multiplied with u1. You will notice that this quantity here is a scalar quantity, so its transpose is itself, and its transpose is simply this. Similarly, this matrix product here, its transpose is this quantity here. So if we subtract the upper equation from the lower equation, we get this here, which is omega 1 squared minus omega 2 squared times u1 transpose m u2 is 0. Now it is obvious that if omega 1 square is not equal to omega 2 square, then u1 transpose m u2 is equal to 0. This is a kind of orthogonality condition with the mass matrix appearing inside as what we call a weighting matrix. In case omega 1 square is equal to omega 2 square, remember that because of our theory of symmetric matrices, we know that there are in fact two independent eigenvectors u1 and u2, and we can always choose linear combinations of them and define new ones u1 and u2 such that this orthogonality condition is still met. So we've got orthogonality now. Now for any r is 1 or 2 or 3, whatever, any r, let us look at ur transpose mur. Eigenvectors can be multiplied by arbitrary scalar multipliers, so we can always scale the u so that this product here is 1. We'll scale the eigenvector. After scaling, if we write all the eigenvectors one by one in this n by n matrix, which we call capital U, then by substitution you can verify that capital U transpose m capital U is identity. So this is the mass weighted orthogonality we were talking about. Also, when we take this equation for the Rth eigenvector and eigenvalue and pre-multiply by ur transpose, set it equal to 0, and we notice that ur transpose mur is 1 by scaling, then we conclude that ur transpose kur is omega r squared. And because k has been assumed to be symmetric positive semi-definite, that is why the omega r squared is greater than equal to 0. If this was symmetric positive definite, this would be strictly greater than 0. If this was not symmetric positive semi-definite and actually had a negative eigenvalue, we would have a negative eigenvalue here, and then in the exponential solution we would actually have exponential growth or decay. To have oscillatory solutions, we require that k is symmetric positive definite or positive semi-definite. I mean, to have all solutions being oscillatory, that's what we require. Defining capital omega square like this diagonal matrix with zeros here again, we find u transpose ku is capital omega square, and this is stiffness weighted orthogonality. So the system of eigenvectors simultaneously satisfies mass weighted and stiffness weighted orthogonality. Net result of this, released at any condition, the undamped unforced system has a solution wherein all generalized coordinates vary in time as linear combinations of sinusoidal oscillations at certain discrete frequencies, with 0 as a special case. These discrete frequencies are called natural frequencies, each such frequency is associated with generalized coordinates varying in certain specific proportions, defining motion patterns which we call mode shapes, and these mode shapes satisfy mass weighted and stiffness weighted orthogonality conditions. Normal and orthogonal are the same. So these, because they satisfy orthogonality conditions, these mode shapes are called normal modes. And structures with infinitely many degrees of freedom will have infinitely many natural frequencies. That we have not proved, but it's true. There is going to be one natural frequency per degree of freedom. Examples of mode shapes, here's one. Two masses identical, one spring and a frictionless surface. So as you can imagine, this can move in this direction with a constant speed that represents no oscillation. Omega squared is 0. Over there, the mode shape is going to be equal movements to the right. So 1, 1 in terms of mathematics, equal displacements to the right. This is called a rigid body mode. There is no oscillation. It has a translation like rigid body. There is another mode where this one moves left and this one moves right by equal amounts, and then the middle of the spring is stationary. So this mass actually sees a spring stiffness of 2K, as does that mass, and so omega squared is 2K over m. Here is another example. This one has two masses and three springs. For simplicity and insight, I have kept them the same, the stiffnesses and masses. So over here, these two masses could move to the right by equal amounts, in which case this spring never comes into play. This mass only sees this spring, and so omega square is K by m. Over here, this mass moves left, this mass moves right, the middle of this spring is stationary. So from here, this mass sees 2K and K here, 3K, as does this mass, 2K here and K here. So the second mode corresponds to omega squared is 3K by m. This one is a double pendulum, and it has one mode where the first mass with the string moves to the right a little bit, and the second one moves to the right even more, and then it would oscillate. So this would go like that, and this would go like that. That's the way it would oscillate, and there would be some natural frequency corresponding to that. And the second mode would look like this. So this mass would have moved right and this one would have moved left, and then this would move to the left even as this was moving to the right, and that is how it would oscillate. That's the second mode. From this double pendulum, you can imagine what a hanging chain will be like. For the hanging chain, the first mode will be the whole chain moving gently to one side, bending a little, but moving like this and then moving like this. It's like a pendulum, only it's flexible. But the second mode is going to be part of the chain moving right and the bottom part moving left. And then when this one moves left, that one will move right. There will be a third mode, still higher frequency, where this region will move right, another region will move left, yet another region will move right, and so on. There is going to be many, many. It's an infinite dimensional system. It will have infinitely many modes. There is going to be one natural frequency per degree of freedom. Here is an Euler-Bernoulli beam. So this is a cantilever condition, and you may intuitively see that there is going to be one mode like this, another mode where this part bends up and this part comes down, another mode where this bends up, this down and this up, and so on. A sequence of natural frequencies and associated mode shapes. This is a simply supported condition, pinned here and pinned here. So the first mode, the whole thing will bend up, then bend down, and so on. The second mode, when the left side goes up, the right side goes down. When the left side goes down, the right side goes up. The third mode, a little bit up, another portion down, another portion up, and so on. This is a special condition which is free. This is just like this system here. It's free. So over here, there is one displacement where it just goes up, and it's a rigid body mode, no oscillation. There is another displacement where it rotates like this, and there is no oscillation either. So there are two zero eigenvalues, associated mode shapes, and then subsequently there are vibrations. So omega 3 is greater than 0, and this one will bend like this with a portion of it going up and two parts coming down. Here is a pinned free boundary condition. This side is pinned, this side is free. So it will have one rigid body mode like this with no deformation at all, and then it will have one mode like this pinned here, free here, up here, down here, and then when this one comes up, that will go down, so that shape, then there will be a third, and so on. So let's do a couple of more examples. Here is a mass M, length L, rigid rod. It's a uniform slender rod. It's supported at two ends by two springs of stiffness K1 and K2, and the degrees of freedom, the generalized coordinates are x1 and x2, the vertical displacements of the two ends. The motions of all points are nearly vertical, all rotations of the rod are small, and we will neglect gravity. The potential energy V is the potential energy of this spring plus this spring, half K1 x1 squared plus half K2 x2 squared, which can be written as half times x transpose times this 2 by 2 matrix, which happens to be diagonal, times x. That's the stiffness matrix. That's the K matrix. Similarly, there is a kinetic energy, and this is going to be half times the mass times the velocity of the center of mass, which is here in the center, squared, plus half times the moment of inertia about the center of mass times theta dot. I haven't defined theta dot, but I am sure you know what I mean. And so this part over here is half m. The velocity of the center of mass, the velocity of this point here, is half the velocity of this plus this. So over here x1 dot plus x2 dot by 2 whole squared. And then for this part, the moment of inertia is ml squared by 12, and theta dot is the rate of rotation, is x2 dot minus x1 dot by L, the whole thing squared. Now you have this, you have your kinetic energy, potential energy, Lagrangian, and you can get Lagrange's equations, you can get the mass matrix, stiffness matrix, find the natural frequencies and the eigenvector. Second example, here is a cantilever beam. The displacement of different points along the beam at different instants of time are all different. So this displacement y over here is a function of x and t. Potential energy is the strain energy. We are neglecting gravity in this example as well. So that is EI by 2. I should write what these parameters are. So let me write here M, L and EI for mass, length and bending modulus. So EI by 2 integrated from 0 to L, that is the total length of the beam, y double prime squared dx. What is y double prime? It is del squared y del x squared. Similarly, kinetic energy is half times the mass of a little element length. So m over L is mass per unit length, and the dx remains here inside the integral sign. And y dot squared is the square of the upward velocity of any point over here. So velocity in the axial direction ignored, rotational kinetic energy of any little section ignored, only translational kinetic energy is retained, and over here only bending strain energy is retained. Shear deformation is ignored. Under this condition, we can derive equations of motion for this as a partial differential equation. That's not what we are going to do here. What we are going to do is approximate this y as a linear combination of three things. So here is one generalized coordinate a1 of t multiplying f1 of x, some shape function that we will choose, plus a2 of t times f2 of x plus a3 of t times f3 of x. If we choose f1, f2, f3 and we leave a1, a2, a3 as arbitrary functions of time, then these a1, a2 and a3 are the generalized coordinates in our approximation for the deformation or deflection of this beam, and in this way we are making a 3 degree of freedom model. This kind of approximation is easy in Lagrangian mechanics and difficult in Newtonian mechanics. Once we substitute these, then we find the potential energy, and it has a1 squared, a2 squared, a3 squared, a1, a2 and so on. And similarly, once we substitute it into the y dot and integrate, then we will have a1 dot square and a2 dot squared and so on. And then we will find the equations of motion, and we can, for example, estimate the natural frequencies. I would like to emphasize that there is an added modeling choice, which is the choice of f1, f2, f3. For example, you can choose, I seem to have lost this line here. For example, you can choose f1 is x over L squared, f2 is x over L cubed, f3 is x over L to the fourth. And the reason we are making this choice is that these choices ensure that no matter what a1, a2, a3 are, there is zero displacement and zero slope at x equals 0, which is required for the cantilever boundary condition. Okay, so that ends this example. I'll just add one line here because we want to move to single degree of freedom. So once we understand mode shapes, once we understand natural frequencies, once we understand how to write the equations for n degree of freedom systems, then we are here now. Let us say mx double dot plus kx is q of t, the vector of generalized forces. Then we change coordinates. We go to modal coordinates. We say let x be equal to u times xi, capital U times xi. This is the matrix of eigenvectors. When we do this and we substitute it in here and pre-multiply by capital U transpose, what happens is we get an identity coefficient matrix. So xi double dot plus capital omega squared xi is equal to, and then over here we have U transpose times q, which is just some q bar. Okay, so q bar has different elements over here, and what has happened here is that because capital omega squared is diagonal, therefore the equation for xi1 double dot plus omega 1 squared xi1 is q1 bar is decoupled. Xi2 double dot plus omega 2 squared xi2 is q2 bar, and so on. All the modal coordinates are decoupled. Each one can be solved separately as a single degree of freedom system, and it is with this motivation that we study the single degree of freedom system quite a bit in the course. I just want to point out, although I am not going to discuss it much in the class, is that this q bar involves pre-multiplication by capital U transpose, which in a way is like taking a dot product with the eigenvector. And sometimes there are interesting situations that arise and you have to think about nonlinear terms and non-ideal behavior. I just wanted to point out this example. For example, if you have a pinned free beam, let us say, so it is pinned here and free here, and this is the nodal point for its bending mode, and it is exactly at this point that you apply a concentrated force. Then if you work out the mathematics, you will find that the q bar corresponding to that mode is going to be 0, because the dot product with that U transpose will be 0. And as a result, according to linear theory, you will not be able to excite this particular mode at all by exciting it over here. But I am not going to, this is outside the purview of our class. I just pointed out to you that although it seems that we can decouple the modal coordinates and look at them one by one, there is implicit in here this issue of taking this U transpose Q, and for most cases it is not important. It just gives you a number and you work with it, but occasionally you can run into some interesting problems.